Good morning and good afternoon and good evening to everybody, and welcome to another session of Expand Your Horizon. Today with us is Mo Alkhadra. Hi, Mo.
Hi, pleasure to be here.
Thank you for joining. Mo is the
Thanks.
co-founder and CEO of Lithios, a deep tech company. We'll hear much more about it in a second. And again, thank you for joining. We know how busy is the life of a startup CEO, and we're really grateful for the fact that you're willing to spend this hour with us. So yeah, maybe before we start talking about lithium and batteries and technology, maybe if you can tell us a little bit about yourself in a few words.
Absolutely. Yeah. Thanks again for having me today, Shai. It's an absolute pleasure to be here with you and with the broader Orbia team as well, and with all of yours. Uh, as you mentioned, my name is Mo Alkhadra, founder and CEO of Lithios. I'm actually a chemical engineer by training, and I'm maybe interested in telling you a little bit more about the origin story that brought me to where I am today, my professional career. So I actually grew up in the Middle East, to a household of physicians. My parents, many of their siblings, and many other members of our family are actually in the medical field. So, in a sense, I'm maybe the odd one out by having pursued a career in engineering, which was actually inspired a little bit by my family's curiosity and inclination to, understanding science and a little bit on the technology side as well. I was always a builder growing up. I used to collect these Legos and other toys, which involved some aspect of assembly to them. We're building or assembling components or parts to build a larger structure or product ultimately. And that sort of interest, I took with me throughout my educational career. I was actually then supported, let's say, or endorsed by some of my science teachers who felt that I had some form of intuition to understanding chemistry. I actually excelled in those classes in high school, actually starting in middle school through high school, and eventually wanted to pursue a career that I felt would be able to really deliver, large impact to the world, but also an opportunity for me to leverage and sort of advance my interests in technology and science. So I actually went to school in UC San Diego, and maybe this is a good opportunity to provide some visuals, where I studied chemical engineering. I actually did a bachelor's and master's in chemical engineering. I spent the vast majority of my time working on my classes and research, so I ended up graduating at the top of my class at UCSD, and pursued academic research in Professor Darren Lapomi's lab in semiconducting polymers. So this is my first exposure now to the energy sector. We were focusing on making flexible and even stretchable solar photovoltaics using these organic or plastic polymer materials. And we had published a lot of papers in the group with my graduate student mentor, now actually a faculty member in Ohio. And we eventually, or rather, I eventually became interested in pursuing a further career in academic research. So I applied to graduate school, applied to probably about 6 schools or so, and ended up picking MIT as sort of the preferred institute for me personally, given its balance of obviously rigorous science and engineering education, plus the opportunity to venture into a wide range of career options, or explore them at least, given proximity to the business school, being in the Cambridge area. Obviously, it's a very dense academic zone, and also just being surrounded by great talented people in general. So I actually took a variety of courses outside of the curriculum, including some at the business school. I actually participated in a number of venture-oriented programs, so to speak, that got me exposed to the entrepreneurial career option. And then I leveraged the research that I was doing in electrochemical ion separations to spin out essentially the work we do today at Lithios, which is focused on scaling low-cost supplies of lithium for rechargeable batteries. And we'll talk much more about Lithios. Just a quick additional point at MIT, we had worked on ion separations using electrochemistry, and that's sort of what got us inspired to commercialize the technology at Lithios. We studied applications like water treatment, waste valorization, like recycling transition metals from waste batteries and catalysts, and ultimately then transitioned into resource recovery, which is now focused on pulling out a valuable target from water rather than removing a toxic contaminant, so to speak. The final point I was going to make here was the Activate Fellowship, which was sort of the transition period for me going from academia into now this entrepreneurial journey, which I received basically toward the end of my PhD. For those who don't know, Activate is a 2-year entrepreneurial program that supports scientists, entrepreneurs to spin out technology, typically out of a PhD program or after some level of experience in industry, with 2 years of support and mentorship to get us started.
I see a minor in mathematical finance. How is that related to electrochemistry or to entrepreneurship?
The truth is, it's not. I actually the funny thing about my journey was that it was very nonlinear. I actually didn't really know that I was going to even go to grad school when I was an undergraduate student, and by the time I got to MIT, I was maybe interested in learning a lot more about a wide range of career opportunities out there, which included academia, industry. I considered consulting. I even put out an application to a hedge fund. Needless to say, it didn't go very far. I don't think I was built for that work anyway. I'm more interested in creating stuff, building and leading teams, and ultimately really took classes in finance, mainly out for personal enrichment.
Right. You mentioned the transition from research and academia into the entrepreneurial and new venture domains. What would you say is the biggest difference between being in academia and being in the venture world?
Yeah, there are a lot of differences. My PhD experiences can vary substantially by institute, by advisor, and so forth. My personal experience was, I'd say, a bit exploratory. I had the freedom of actually looking at a wide range of ideas, testing them out, testing hypotheses. I was actually an experimentalist, probably one of the only experimentalists in broadly a theory-focused or computationally focused research group at MIT, which is quite uncommon. And so, I had the freedom to really do a lot of different things in the lab, working with now my co-founder, Professor Martin Bazant, who was my advisor in the chemical engineering department at MIT. What we're doing at Lithios today is now very fast-paced. We're in a cutting-edge space that is undergoing a significant revolution, let's say, in the lithium industry, with growth rates expected to exceed 7 to 10x in the coming 2 decades. So there isn't much room for that kind of exploratory work anymore. Now we're very focused, on a single technology with a single application in mind, so to speak. And we feel now the pressure, urgency to deliver on that sort of claim.
Great. And maybe just last question before we dive into lithium and extraction. What are the 2 things that Google wouldn't know about you?
Yes, Google knows a lot. I don't know if there is much that they don't know at this point, but a couple of things that would come to mind. I actually hate, I know it's a strong word, but I hate carbonated water. I only drink 2 things. One is still water and the other is milk. Actually, don't drink much else for that matter. Juice, juice, beer, alcohol, anything like that. It's not really my thing. The second, maybe I would say, is I've never had a sleepover actually growing up. Always ever resided at a family member household. So could be something I missed out on. But
you never had people coming over. You never went to people's house.
Both ways.
Okay.
Either way, it's not been part of my experience, which I've always wondered what that was like. I've seen it on the TV before, but those are probably 2 things Google will likely never. Now they must know though after the Teams call. So we'll see, or maybe Microsoft knows.
Good. Okay, Mo, thanks for the detailed introduction, and maybe let's jump into Lithios and try to understand what the industry is about, what problems we're trying to solve, and how Lithios is doing it differently than other companies. And I will allow myself to interfere in the middle if there are any questions or clarifying points that we probably want to make.
Absolutely. Yeah, so maybe I can start, Shai, by mentioning that, our journey began just after I mentioned receipt of the Activate Fellowship in 2022. And at the same time, we actually got some venture capital investment from one of the leading VC firms in the climate and energy space, which is Lower Carbon Capital, and a few other smaller checks from family and friends and a couple other VCs. So that funding got us started to build out and carry out the R&D around our core technology, which I'll talk about as well in great detail. And then I'll mention how that R&D work ultimately led to a larger seed round led by Clean Energy Ventures, which is now also on our board, helping us grow and scale the team and the company to eventually get to pilot projects. But let's rewind a little bit and talk a bit about the lithium industry and how we even thought that we could compete or even provide value to this industry. So I don't think it's a surprise to most viewers that the lithium industry is undergoing explosive growth in demand, and we anticipate the need for hundreds of new projects by 2040. And these are hundreds of substantial, large capital projects. And that stems from the fact that there's significant growth in demand for electric vehicles and for the critical minerals that go into the rechargeable batteries used in those automobiles. So the lithium industry since 2020 will have to have undergone about a 14x increase in size by 2040. And this will require dozens of new projects in the near term, and then eventually hundreds of new projects by 2040 if we anticipate to meet that demand. And what these circles show you are the fraction of unavailable supply expected in those coming years. And the reason for that lack of supply in our perspective is the inadequacy of current lithium mining processes to scale lithium supplies. And we'll talk about what those processes are. On one hand, that may pose an existential threat to the industry, but on the other, it actually presents a very exciting opportunity, rather, from a financial standpoint and from just a commercial innovation standpoint for new technologies to begin to address this challenge. And it's our belief, actually, at Lithios that the world has ample lithium resources underneath its surface. It's just that the current methods used for lithium production today are not fit to scale that supply.
I think if I'm not wrong, I read that 2 weeks ago or 3 weeks ago there was a huge underground asset that through some exploration in the U.S., where was the Wisconsin, if I'm not wrong, that they found a huge reservoir, right?
In the Smackover.
Yeah.
You're referring to the one in the south. Yeah. So yeah, that's a good point. And again, is directly aligned with our perspective that the world has sufficient lithium resources. The problem is in turning those resources into something valuable. So there was actually the news you're referring to, I believe, was this I guess adjustment in the measured resource size in the Smackover region, specifically I believe in Arkansas. Yeah. Possibly even in Texas. And there were other discoveries, I think, in Pennsylvania from produced water, Salton Sea in California in the US, and even outside the US, as a matter of fact. And so, going back to the methods used today, there are two real types of resources or formats from which lithium can be produced broadly. One is hard rock and clay. I'm sort of lumping that into one category as a mineral ore type. And the second is from brines. And those are two very different formats. And within those formats, there's a whole wide range of grades and compositions and resource types that add sort of flavor, let's say, to the lithium production process. But starting with the rock and clay route, this is probably the image that comes to mind here on the left when you think of a typical open pit mining process. It involves excavating rock, leaching it into a acidic concentrate, which then gets refined through an extensive downstream processing train. And I think about 50% or so, maybe off by a couple percentage points, of lithium today is produced from this route. I believe to the greatest extent from the west, in the West Australia region, with refining done actually overseas in mainland China. The rock and clay mining process is extremely environmentally impactful with a huge carbon footprint and generally significant damage to the landscape where that rock or clay ore is mined. The mining process here also has very lengthy permitting processes or timelines, so to speak, that make it very difficult to bring up supply sort of on a demand basis. And so we foresee significant challenges in actually using this route on its own to scale lithium supplies. More so, there's only about 25% of lithium resources exist in this format, which means that there's a much larger share of potentially viable lithium resources in the brine format, which I'll talk about in a moment.
Rock and clay, sorry, rock and clay is what sometimes people refer as spodumene or something like that?
Spodumene, yeah. Spodumene is a hard rock pegmatite ore type. And of course, clays is what I'm viewing or considering personally as your frontier sort of emerging ore type, in the sense that these are not mined today, or they're on the cusp, let's say, of being commercialized through projects by, for example, Lithium Americas in Thacker Pass and others in the US and elsewhere. I believe there's a project Rio Tinto is looking to develop on a mineral type called Alkhadra in Serbia. But yeah, typically today, I believe the majority of this category falls under the spodumene type, so to speak. And that's typically your highest grade, highest lithium concentration, or typically it will have the lowest levels of impurities relative to lithium compared to other clay types, which are what I'd consider lower grade mineral ores. Yeah. And despite that, given the complexity of the mining process, you will see a significant cost premium, so to speak, compared to the brine evaporation process. And that's true even for the highest quality integrated projects, typically. And for non-integrated projects or for lower grade deposits, that premium increases significantly. And the majority of the additional lithium supply that came online in the last couple of years actually was in that low grade category at the rightmost part of the lithium cost curve. And so this brings us really to the second type of resource or format, which is natural brines or saltwater brines, which are typically water deposits found underground to a large extent today in Chile, Argentina, and to a lesser extent in the US, although that supply is hopefully coming up now with the development of new DLE technologies, although that's different from the evaporation process you see here. The only way today by which, or nearly the only way by which lithium is produced from brine is through evaporation in these massive surface ponds, where brine is pumped from underground into these huge pools of water, where the brine sits for up to 2 years to evaporate passively under the sun. And that up-concentrated slurry is then refined into the battery powders, like a carbonate or potentially a hydroxide. And I think for scale, just to show the magnitude of these projects, this is a single project, mind you. It's one of the largest, as a matter of fact, but still, this red rectangle here in the center is representative of the size of Michigan Stadium, the largest football stadium in the country, or Camp Nou in Spain, which is also one of the largest soccer stadiums, I should say. It's not even just the field, it's actually the full stadium. To show you the sense of the size of these kinds of projects. And these are the projects which we need hundreds of by 2040. And there's really not a viable way, in my opinion, to scale these. In addition, these are geographically constrained. They're climate sensitive, obviously requiring very high elevations, low precipitation, arid climates. They have severe environmental impacts on the underlying landscape, produce significant quantities of solid waste, and consume huge amounts of natural water resources. In addition, they're actually quite wasteful on the lithium side as well, with less than 50% yields typically for a brine project. And most importantly, in our opinion, is that they're limited to high-grade brines, which have very high lithium concentrations and low levels of contaminants. And let's dive into that a little further here. The typical way lithium is produced from brines from these ponds, which, as I mentioned, require high lithium concentrations. Typically, we're talking here in parts per million or milligrams per liter. And typically, that would be about 2,000 ppm for some of your highest grade brines. The ponds that I've seen have gone as low as maybe 500 or 600 before being considered, uncompetitive. And they're very sensitive to the levels of contaminants present in the brine, typically measured as a ratio of, say, magnesium or calcium to lithium. There are many other contaminants, but these are the most prominent and ones that require the greatest use of chemical reagents to remove in the post-processing train of the refining process. And so what's accessible today is present here is shaded by this gray region in a very narrow part of the resource chart. And about 75% of, or excuse me, 80% of all known deposits are now completely out of reach using the only really available method for lithium extraction from brines.
Just to make sure, no, we maybe play back the data in simple words. We're saying in those brines, and brines we mean salty water in simple words, what they have inside is a lithium concentration, which at best is 2,000 ppm, and in many cases even lower than that. We talked in the past about 700, 500, even lower than that, 60, 70 ppms. So just for people to understand, 60 ppm, it means 60 parts per million. So there are millions of other things in those brines that are not lithium, right? Obviously there is water, but there are also other materials like magnesium, like calcium. And again, you want to extract lithium, which only makes a very, very, very small portion of that body of water.
Correct. Yeah, so I think the best way to think of the implications of this brine composition, let's say, on the cost, right, measured in terms of lithium concentration and let's say contaminant levels, is the lower the lithium concentration, the larger these ponds have to get. And the scaling is actually faster than linear as you diminish lithium concentration, meaning as you get to, this is probably an 1,800 average, or maybe even 1,600 ppm resource measured over the life of the mine. As you come down to, say, 60, you may now need much more than 10x the area of pond to process that same quantity of lithium measured on a throughput base. And your cost will now scale in a way that makes that very much uneconomic. So the impact of concentration is significant, and it becomes, the significance accelerates, let's say, as you drop below 400 to 500 ppm, right here, basically. On the impurity side, the impurities really affect your post-processing to the, of lithium for the most part, in the sense that as you take lithium brine through these sequential stages of ponds, I forget if it starts on the right to the left, or maybe it's from the left to the right, as a matter of fact. And once you get to the end of these ponds, you essentially have to remove everything else subtractively to isolate the lithium and then crystallize it as a carbonate, if that's the typical route. So the more contaminants you have, you need to add significantly larger quantities of chemical reagents, usually a base or some form of alkaline, to precipitate these problematic contaminants that interfere with the battery grade specifications required for manufacturing. So the cost will then scale on the operating side, on the OpEx side, with the ratio of contaminants, and the lithium losses will also scale, since lithium tends to co-precipitate, be removed with some of these contaminants, depending on the conditions. And so, this is a challenge that we've observed at Lithios. Admittedly, we're not the only folks that have seen this. Obviously, people have been working in this space for much longer than we have, developing technologies that I think are very familiar now to the folks in the industry, referred to as DLE, or direct lithium extraction. And this is essentially a suite of either chemical, membrane, or electrochemically based techniques used to selectively separate lithium from brines without the need for evaporation ponds. Now, there's in the lithium industry one project, I believe, that's commercial, operated previously by Livent, now called Arcadium, which uses a hybrid pond adsorption process. So they begin, I believe, either with the adsorption technique first, followed by enrichment in large ponds. And that is not what I would consider true DLE, which would require the complete elimination of ponds and the reinjection of spent or lithium-bearing brine following the extraction process. More recently, we've seen a major French mining company called Eramet actually begin the commissioning of the world's first DLE plant in Argentina. And we're very excited to actually see the output of that project. But we admit that it's taken them, a very long time to actually develop the technology, qualify the mine resource, and ultimately deploy and commercialize the DLE plant. And it's no simple feat. It's a very impressive actually output by their team. And we hope to deliver at Lithios a competitive technology that can unlock additional resources outside of South America, specifically, where basically all brine evaporation processes have taken place to date, or lithium extraction processes from brine, I should say, have taken place now with the addition of this adsorption technique by Eramet. So we're looking at markets, obviously in South America. We have a very strong interest in North American resources as well, and Europe, and potentially other markets at the right time. So at Lithios, we've taken a bit of a different approach. We have an electrochemical technique, not quite like the adsorption process, which we'll talk about in a moment as well. But our approach and focus has not been to compete with these high-grade pond-based projects, but rather now to unlock this sort of untapped market of low-grade brines, which will have very low lithium concentrations and very high levels of contents. And our goal is to turn these uneconomic brines into low-cost lithium at costs comparable, or let's say competitive, with some of the typical pond-based projects and even the traditional spodumene-based mining processes. And our approach took inspiration, I think I mentioned briefly in the intro, from some of the electrochemistry and electrochemical work that I've done during my PhD. We've looked at other techniques in the industry that have had tangible impact on our day-to-day lives, from the production of chemicals to metals processing and ultimately energy storage and distribution. And we're developing Lithios ALE, advanced lithium extraction, to really become a top method for the production of lithium from low-grade brines and other unconventional sources, let's say, which we'll talk about as well in a bit. So our method here is based on the concept of an electrochemical reactor. We call it ALE to differentiate from the typical chemical-based DLE processes, because our technique is quite different. In fact, we use a system which has an architecture that is akin maybe to an electrolyzer or a flow battery, comprising parallel plates coated with capture material that can selectively extract lithium from a flame. So the way this works is a brine will flow into the stack through the individual layers of this device. And inside these layers, lithium ions will find their way to a reactive surface where they will bond, essentially. Once the capture electrodes have been filled with lithium ions, the process is paused to discontinue the flow of brine and switched with a flow of clean water into which the stored lithium ions are released. So it's a two-step process of capture and release. Following the release step, we produce a purified lithium concentrate with very high concentrations of lithium and very low levels of contaminants that can then be readily refined into the battery chemicals used in manufacturing. And both the capture and release processes are driven by the input of only electricity and a very small quantity of clean water. So this is
the process is based on the electrical affinity of the lithium ions that are positively charged, I assume, with the negatively charged plates of your stack. And this affinity extract the lithium ions from the brine, and then when you wash it with clean water, you basically get clean water plus only lithium.
That's right. Yep. And this process, is driven by, the selectivity here is twofold. You touched on a great point, Shai. One is the design of the materials, which are very much compatible with the properties of lithium ions, which, they're very small, typically the smallest metal on the periodic table by ionic radius, and they are monovalent ions. And so they have a very natural thermodynamic pathway to bonding with the electrode or reacting with the electrode, as you had mentioned. Second is, this is an electrochemical process driven by voltages and currents, and that affords additional selectivity by gating, essentially, or controlling the interactions of other ions, such as sodium, magnesium, or calcium, which are most proximal to lithium on the periodic table, from entering into the electrode as well. So we can control that to a much greater degree than what you would find in a typical chemical-based DLE process. And why is selectivity so important? Well, the reason is that the more selective you are for lithium, the less quantity of contaminants you'll have in that ultimate lithium concentrate, which means you'll have a lot fewer unit operations potentially downstream to reduce cost of the refining process. And at the same time, we have the ability to produce a much higher concentration recovery solution, which affords us an easier pathway to enriching the lithium concentrate for refining as well, without the need for, say, very extensive equipment or enrichment technologies, let's say, to get to the ultimate end product. So those are really the key attributes of the system. I should also mention that most people, when they think of an electrochemical process, they may be worried about the high energy input to the system. Our energy inputs are extremely low. Typically we probably can't cite the exact energy metric, but I can mention a range, or a bounded at least, to say that it's below about a megawatt hour per ton of lithium carbonate, which is a very low energy requirement, I'll say. Much lower than what would be needed, for example, by a chloralkali process to make acid and base, say if you're using an ion exchange DLE process, and it would be a lot lower than the heat required to preheat brine if too cold, for instance, as is typically required for an absorption-based DLE process. So ultimately, it's a very water efficient and a very energy efficient process with very high lithium selectivity.
So basically, you don't require any pre-treatment of the brine. You just put them through the stacks, and so the selectivity takes place in the stack.
It's a great question. I wouldn't say we require no pre-treatment, but we require very little pre-treatment. It's a great segue actually into the next slide, which gives you a sense of where Lithios' technology fits in that full process flow sheet. So it typically begins by pumping brine from underground to the surface, after which it is flowed through our capture reactors to produce that purified lithium concentrate that then gets refined ultimately into a shippable product. Regarding pre-treatment, typically the brine, and it varies dramatically by region and by composition, but generally speaking, there are certain properties of the pumped brine that have to be met to maintain the integrity of the downstream processing steps, obviously including the ALE capture step as well. And typically, we would like to avoid the passage of, say, suspended solids through our systems. So there would be potentially a small or brief filtration step. There, in certain applications, may be dissolved gases that would be toxic or could lead to toxic exposure to an operator that we would like to have removed prior to processing. And so those are the kinds of generic pretreatment steps that you would have to do, whether using a DLE process or ALE. But we have no further constraints in terms of the type of dissolved species present in solution. And we have a pretty flexible range of operating pHs and temperatures that make the system quite versatile for different applications.
And then what do you do with the byproducts or the waste? And your answer might differ whether we're talking about things like I don't know, magnesium, or if you talk about things that are a little bit more toxic?
So in terms of byproducts and wastes produced, generally every process will have some form of waste generated. And we're talking specifically about the ALE step. Obviously, there could be some small quantities of liquid waste produced from that recovery solution upon dewatering or crystallization, for instance. And there may be some solid waste generated in the polishing step. Typically, it will be a metal carbonate or a metal hydroxide, potentially, depending on the type of chemistry used for polishing. But ultimately, that waste will have to be discarded. What's maybe advantageous about our system is that it produces a lot less of compared to a competing DLE technology. And the way that to rationalize that is by the fact that our selectivities are much higher, which means that the quantities of, let's say, divalent competing ions that pass into this downstream processing train is much smaller. And so the amount of polishing needed is much less, and as a result, the amount of solid waste generated is significantly lower than what you would get otherwise. And I'd say for ALE, it's lower than for a competing DLE process, and both of those are much lower than a typical pond-based process, which normally has to remove the full quantity of all other competing species present in the brine. And that's why those pond projects are typically limited to very low magnesium to lithium ratios in the industry. And they typically have to have very high starting quantities of lithium, again, to manage the levels of waste produced, among other things.
Yeah. And if just to understand the magnitude and the efficiency of the process, if the incoming concentration is, let's say, I don't know, 1,000 ppm or whatever number you wanna share, what is the concentration after the ALE process?
Yeah, that's a great question. We have the opportunity to enrich the recovery. We call it the recovery solution. The DLE processor would call it the LU8. But in either case, that recovery solution can be enriched by ALE up to several thousand parts per million. I can't necessarily disclose the exact figure, but we've been testing at multiple thousand ppm on the recovery side, starting with brine as low as maybe even a couple hundred ppm, less than 200 ppm. And again, I'm keeping these ranges broad, not necessarily to commit to a specific figure. But by having significantly higher enrichment as well, that comes maybe to this important point, is that these dewatering steps, and by the way, dewatering here usually involves either reverse osmosis, some form of thermal evaporation, or maybe a combination thereof. And that would be significantly diminished without with the ALE process, by having a much higher concentration recovery solution.
So all the steps after the Lithios ALE step that we see on the screen, dewatering, polishing, to crystallization, these are all existing known processes in the industry. Once you give them the lithium with the brine with lithium only, these are known processes, right?
Correct. Basically, these technologies are commercial. We mentioned RO, thermal evaporation, crystallizers sold by big, water solutions companies or other equipment vendors. On the polishing side, probably will be, precipitation tanks or ion exchangers. And then on the pumping and pre-treatment side, that's typically done by an experienced either oil field services company or well field services company with experience in oil and gas. And I'll say that the brines being pumped for the lithium extraction application are much shallower wells, let's say, that need to be developed compared to a typical oil and gas, or a complex, let's say, oil and gas operation, which makes for an overall readily amenable pumping process. On the pretreatment side, those will typically be ultrafiltration modules or some form of membrane filtration technology, which again is used extensively in the water treatment industry. I'll say most of these steps actually exist to a large extent already in the water treatment industry. I think the lithium space is now capable of adapting a lot of those tools to use for this new application as well. And in fact, a lot of these are also already used in the downstream trains of both rock and brines, although they will look a little different for a DLE or an ALE type process.
Yeah, and maybe last question on this slide. And our audience today, many of them are chemical engineers and have operated electrolyzers and other electrochemistry type of processes. So one question that came in is about potential fouling of the electrodes because of whatever contaminants or other electrochemical processes that might affect the electrodes themselves.
Yeah, that's a great question. Very, very common for us to think, to be asked that, and we think about it quite regularly. So the requirements on fouling for us, as I mentioned, we have to remove suspended solids. Those will typically accumulate and eventually clog or destroy the electrode material. Frankly, they would also destroy any of the downstream processing steps by either abrasion or accumulation in membranes. So it's best to have those removed. Other dissolved species, let's say a transition metal, manganese, iron, copper, for example, may be found in small quantities in some of the US-based geothermal or oil field brines, potentially even produced water, which could have negative impacts on our materials. But we've designed our electrodes and we operate them in certain regimes, let's say, that preclude any kind of parasitic reaction with these foulant species. And by virtue of controlling the voltage and current of our system, we can regulate what types of electrochemical reactions take place. Further improving the selectivity for lithium, also mitigating potential impacts of fouling at the electrode surface. And that's a great feature that I think is unique to our system compared to DLE, which may be at the mercy, let's say, of some of the species coming in. If you have trace iron quantities or manganese or zinc, those could potentially foul the ion exchange sorbent or the absorption media with limited ways, let's say, to mitigate those kinds of unwanted reactions, except by pre-removing those species, which adds to pre-treatment costs and potential lithium losses down along the way.
Yeah. So the life cycle of an electrode would be, let's say they operate 24/7. You expect them to be replaced every so often, or this is like years of life cycle?
Yeah, the goal is to have these last for several years. Difficult to pinpoint a figure here publicly, but what we would say is that these materials will last for a good bit of time before needing replacement. Typically, the electrodes themselves could be replaced while retaining the balance of, let's say, the stack or the system around it to reduce operator input and complexity of that material replacement, let's say. I'll just say that a big part of our focus on the R&D team here at Lithios is to really bring up the lifetime of our material by adapting known techniques used in the battery industry, in the electrolyzer industry, also in other areas which have done significant work in the last couple of decades to bring up the lifetimes of their materials. We operate in a much, let's say, gentler window of conditions compared to an electrolyzer, which will typically operate at very high current densities with potential side reactions that could affect negatively the electrode. In our case, we're operating a much gentler process just by virtue of being in a lower concentration brine environment, and we are very mindful of the lifetime and its implications on ultimate process cost.
Yeah, and Orbia operates one of the largest chloralkaline electrolyzers in Europe. So, and I think I don't remember exactly the number, but we need to replace or maintain the stacks every couple of months.
Right. Yeah, that to me is fair given the extreme conditions, from pH, pressure, temperature to the production of gases, which obviously adds a lot of complexity, and ultimately the densities that a chloralkali or a hydrogen electrolyzer will typically operate at. Could be a couple of amps per cm squared typically. And we're I'll say much lower than that in terms of current density.
Yeah.
So with that said, I'll just very briefly touch upon how we would work with a brine developer, for instance. And generally, there's a lot of detail here on the slide, but the simple story is that we are a technology provider, and we would normally partner with a resource owner through some kind of agreement, be it licensing, tolling, or JV. We provide equipment, potentially additional balance of plant components as well, and maybe operational experience of our core technology to collaborate with some form of resource owner, which could be a brine developer. We haven't talked about it so much on this podcast, Shai, but we've talked previously about potential battery recycling applications as well, and capturing lithium from stranded assets or unconventional resources in the rock and clay mining space as well. Since those processes typically will have a lot of losses, lithium gets trapped in some low-grade brine type concentrate that we could ultimately process for additional recovery and yields. And together we would produce recover the lithium and produce a battery chemical, either carbonate or hydroxide typically, that would be then delivered to either an auto OEM or a cathode producer, battery manufacturer. It's probably worth noting that this effort is very much a team effort by many folks with very diverse backgrounds, I'll say, that are now sort of leading the charge on this ALE, electrochemical-based lithium extraction process. We started out actually, Martin and myself, out of MIT. We brought on Mike Wang as our first member to the team, who now leads the R&D effort at Lithios. And we've since grown the team sort of incrementally, let's say, following our pre-seed round back in 2022, and more recently with our 12 million seed, which has allowed us to double the team. We're about 18 members at the moment, scaling to, I'd say, about 25 in the first half of next year. We've now also operationalized the team by bringing on Vicky and Anna, who sort of head our operations at Lithios. And then on the customer-facing side, we have Omar and Oscar leading business development and strategy. And we have a much larger team on the R&D side, and more recently hiring on the engineering side to help with stack development and process design and pilot project engineering, let's say, and eventually commercial project engineering. So, all of this was made possible by the sort of conviction and generosity, really, of our venture capital partners and investors. Should give a special thanks to Clean Energy Ventures for leading our seed, as well as Laura Carpin for leading our pre-seed, investing in our seed. And we've also brought in several key strategic investors that I think are worth calling out, including Tech Energy Ventures, the venture arm of the Argentinian-Italian oil and gas company Tech Petrol, part of the Techin Group. GS Futures, part of the South Korean conglomerate GS Group, both of which I would say are steeped in the lithium value chain in different segments, let's say, of it, including lithium extraction from brine specifically. Tech Petrol acquired a couple of lithium assets in Argentina recently, and GS Energy and GS Group in general are partnered with, have a joint venture with POSCO, and are collaborating with battery recycling companies and brine developers as well. So these are all very much value-adding investors, in addition to some of our other partners like Mass CEC, Activate, ARPA-E, from whom we recently won actually a roughly $500,000 Sparks Award, and then some of our other pre-seed investors as well. I think it's probably worth mentioning some of our recent features in the news. So we actually completed our seed round a couple months back, but only made the announcement in October, as we were looking to bring on an additional, let's say, funder, which is Silicon Valley Bank, through a $2 million venture debt facility. And we made the announcement recently after having grown the team and relocated to our new facility out in Medford, Massachusetts. So we previously were residing at the Engine, which is a great startup company accelerator based in Cambridge. It used to be both a venture capital firm plus the accelerator, eventually split into two different entities. But we were with the accelerator. We still have actually space there, but relocated to Medford. We had about an 8,000 square foot facility with the intent to expand that to close to 10,000 actually soon, with added space for growth. And we also held an opening ceremony, as you see here, hosting climate tech leaders from ARPA-E, from the Office of Economic Development. We had the mayor of Medford join us. Actually, it was great. And then my co-founder Martin, Dan Goldman, our board member, and Elizabeth Kennedy at Activate, also supporting with this event. So we have a long road ahead of us. We have a lot of work to do to get this technology ready for field deployment in 2025. That's sort of our intent. And from there to get to our first commercial project a couple of years after that. It'll take a village, as I always say, from our team members, other stakeholders, investors, and partners. But we believe that we have a very advanced and differentiated technology with a lot of key attributes that separate us from what's been under development for a long time now in the DLE category. And that's sort of testament to that is the conviction some of our partners have in the technology we're building. They're willing to pilot with us and trial the technology in the field. Next year, we have a couple of pilot projects lined up. We'll be making announcements as ready and appropriate about those. And from there, we would then begin discussions for larger commercial projects to produce thousands of tons of lithium carbonate before the end of the decade.
Great. So I just want to remind our audience that if you have any questions, you can punch them into the chat box. Some people have already asked questions during the presentation, and I'll just go through some of the questions that already been asked. Can you give us a sense of the costs to produce a ton of lithium carbonate, or any KPI that is used by the industry, and how would you compare against producing the same ton using other DLE technologies, or even compare it to existing technologies, even though we're talking about high concentration, either brines or rocks?
Yeah, that's a great question. A bit of a delicate one here on the cost, but obviously I can answer maybe in broad strokes. So the way to it's really difficult to pinpoint cost for to cover basically all resource types. It'll vary significantly from project to project. It honestly may even vary within the same geography and within the same rough acreage, just depending on accessibility to freshwater, power infrastructure, roads, for example, or other methods of transport. But what I can tell you at a high level is that if we were to make a one-to-one comparison with a brine evaporation process in this category of low-grade brine, say take the median resource here with tens of magnesium per unit of lithium, and call it 300 ppm on the concentration side, that could be maybe even a 5 to 10x cost reduction on a levelized basis. It's significant, and I understand that some people may not believe the number, but the truth is the only reason that number is so high is because ponds would never even be attempted for a brine type of this composition. And that's fair to say. So the comparison then would be against DLE. DLE will offer a significant cost advantage compared to brines on a low-grade resource, but still the costs we view are elevated by virtue of requiring huge quantities of either freshwater or power, and in certain cases, the use of significant quantities of chemical reagents or potentially solvents. And so the cost reduction there could be anywhere from potentially 25 to 50% on a levelized basis.
Yeah,
and that's an average for a typical brine. Obviously, without specific details, it's impossible to pinpoint the cost. One thing I will say, Shai, very quickly, is that we're currently in the process of carrying out what you would consider a scoping study or an FEL1 with a major EPC to evaluate those cost comparisons, and at the right time we'll be able to disseminate some of that information. But we anticipate favorable cost reduction relative to peers.
Yeah, and that's when you're taking into account the levelized cost, so capex and opex, right?
That's right. Yep.
And if you compare capex only to other DLE technologies, I imagine you're also favorable.
Yeah. So the cost reduction here I don't know if levelized cost of lithium has been made a thing yet. Typically, people think of the cost curve, which typically shows your fully allocated cash costs, mostly OpEx, but it will have other parameters as well. But it may exclude CapEx, as a matter of fact. And so that's fine for an existing operating project to know whether or not you're sort of on the margin, or you're going to shut down the operations, or maybe wrap up production. For new projects, CapEx matters a lot, and it dictates the facility of financing. It dictates, and it hinges largely on whether or not the technology is bankable. And so we've seen CapEx serve as sort of a gating function, or an inhibitor to some extent, for a lot of new DLE projects. And that's a result of many things, one of which obviously is the high CapEx associated with a DLE project. And that goes without a doubt, compared to ponds on a high-grade resource. Now, we need to find technologies and projects for which the CapEx will be competitive, obviously also the OpEx, but now on low-grade brines as well.
Yeah. So we have 1 minute left, and maybe last question. If you think about the journey that you need to undertake in the next 2, 3, 4, 5 years, what are kind of like the most pressing, complex challenges that keeps you awake at night?
Yeah, it's a great question. I'm sure if you ask every member of the Lithios team, you'll probably get a unique answer from every person. The technologists are obviously focused on the technology. The BD strategy folks are focused on getting that next commercial contract. For me, I have the privilege of being stressed out by all of them. Kidding. It's actually really a privilege to be able to have that vantage point and to get exposure to all of the challenges and complexities that the company and business are undergoing. It's with startup companies and small businesses, it's always a volatile experience. Some days the technology is a true bottleneck. Other days it may be on the customer side. And some days for me personally, it might be on the fundraising side, frankly, on financing. So with lithium prices currently where they are, I anticipate financing will definitely be challenging for new projects, in the sense of trying to overcome that capital cost requirement for new projects to be deployed. Fortunately for us, we are not focused on financing a major commercial project at the moment. We're in tech development mode. So those are taking the front seat, and we, will eventually have to come to terms with the fact that lithium prices may be a bit lower than what has been anticipated in the industry. And that's okay, because our ultimate vision, and it's always been the case, is to develop the lowest cost solution for lithium production from low-grade brines. It's without a doubt that the lithium industry is growing, and it's also without a doubt in my mind that ponds and rock mining will on their own not suffice to close that gap. So yeah, I'll say, in short, we're focused on technology at the moment, and keeping in mind potential challenges down the road on the financing side for commercial projects.
Great. Well, Mo, again, thank you very much for taking the time and the efforts to
Pleasure.
Join our webcast. And, we've been in touch for quite some time now. And, we first want to wish you all the success in the world, and also extend our offer that if we can help with our knowledge and expertise, we're here to support you. So good luck in the important journey that you're undertaking.
Appreciate it, Shai. We'll take you up on that offer, and really thanks again for having me. It's a pleasure to be here with great turnout. A lot of folks on the call. I wish you guys all the best as well in your work at Orbia, and hope to be connected soon.
Thank you very much. Take care.
Pleasure. Thanks, everyone.